Hi, I'm Jess Chellino. I'm a PhD student at the University of Florida working with Saxlepian, and today I'll be talking about analytic covariance matrices for parity violation searches with the 4PCF. It's important to search for parity violation in large-scale structure because if it's detected, it would imply new forces during inflation. And this is because the initial density perturbations are a Gaussian random field, and everything we know about gravity and galaxy formation is parity symmetric. So if we detect parity violation, it would imply something that we currently don't know about going on during inflation. A parity transformation in 3 dimensions is equivalent to a mirror reflection and a 180-degree rotation, but if we use isotropic basis functions, we can average overall rotations, and this makes the parity transformation a mirror reflection. The 4-point correlation function measures the excess clustering of tetrahedra compared to what we would expect from a random field. Tetrahedra are the simplest 3-dimensional shapes that are sensitive to parity transformations, and that makes the 4PCF the lowest order correlation function that we can use to search for parity violation. The tetrahedron on the left side of the page has a primary vertex or a primary galaxy at this red dot, and side lengths R1, R2, and R3 drawn to the 3 other galaxies that form the tetrahedron. R1 is the shortest side length and R3 is the longest. And we define the orientation of a tetrahedron as the direction you travel going from the shortest to the longest side length. So for the left tetrahedron, the orientation would be clockwise. If we take the mirror reflection of this left tetrahedron, we get the right tetrahedron. The right tetrahedron has a counterclockwise orientation. So from this, we can see that the orientation of a tetrahedron will flip under a parity transformation, and that allows us to use the 4PCF to search for parity violation. We can separate the 4PCF into even and odd modes using isotropic basis functions. The even modes are parity symmetric, so we're really just interested in the odd modes. The odd modes should be 0 up to noise, so if we are able to detect a non-zero odd mode, that could indicate a measurement of parity violation. It's really important to get the covariance matrix right when we're detecting these non-zero odd modes. If we have an inaccurate covariance matrix, we could come up with spurious parity violation detections. And we really need the inverse of the covariance to optimally weight the data. Normally, the covariance would be obtained from mock catalogs, but if we have a high dimensionality of observables, this is prohibitive. We really need as many mocks as the dimensionality of the data vector to be able to smoothly invert our matrix. For the parity violation search done with BOSS, it was independent of a model and had about 18,000 degrees of freedom. We expect that other parity violation searches will also have a similar or higher number of degrees of freedom. And so obtaining a covariance matrix from mocks will be quite challenging. So instead, we can use an analytic covariance matrix. In the Gaussian random field limit, this assumes that all the clustering is captured by the 2-point correlation function. And if we take the leading order result based on that, we can obtain an analytic covariance. We can calibrate this analytic covariance with mocks, leaving the number density and the volume free. And a benefit of an analytic covariance is that we can mitigate sampling fluctuations that would arise if we had a covariance drawn from mocks. So I'm working on an analytic covariance for the 2, 3, and 4 PCF, although only the 4 PCF would be relevant for parity violation searches. And this requires integrals of the power spectrum, which traces the clustering of matter as a function of scale or wave number. If we are able to evaluate these power spectrum integrals, we can not only get a better understanding of the structure of the covariance matrix, but also hopefully use it in future parity violation searches. Now, there are 4 main steps for these analytic covariance matrices. The first is to come up with a suitable model for the power spectrum, then track that our model for the power spectrum is okay to use by numerically determining the 2 PCF covariance. Then we use the power spectrum model in our template for the analytic covariance. And finally, we evaluate integrals of the power spectrum to get the analytic covariance. So the first step is to model the power spectrum. We model it as some amplitude over wave number plus a shot noise term. We have found that the most optimal amplitude is 509 h inverse megaparsecs squared, and we use the Boss number density for this. We compare our model to the true power spectrum, where the true power spectrum is from the code for anisotropies in the microwave background, using the values from Planck 2018. The plot on the left shows just the physical part of the power spectrum. So the red dashed line is just our A over K part of our model. The blue solid line is the power spectrum from CAM, and then the black line is the shot noise term, the 1 over number density term. All three of these lines include Gaussian damping to prevent Gibbs phenomenon. The plot on the right is the power spectrum from CAM and our model power spectrum, both including the shot noise term and Gaussian damping. For our power spectrum integrals that we're going to be evaluating analytically, we do include the shot noise piece in them. So we can see that our model and the CAM power spectrum match up pretty closely, except for at lower wave numbers. But as I'll show in a couple of slides from now, this deviation turns out not to affect what we're doing too much. When we evaluate the power spectrum integrals that are needed for the covariance matrix, we need to integrate them against the Jacobian k-squared dk. So the plot on the left is showing this k-squared weighting for the power spectrum. If we take the derivative with respect to k of ln of k, we can rewrite this Jacobian k-squared dk as k cubed times d ln k. And that allows us to get a uniform per dex weighted power spectrum, which is plotted on the right side. Now, both of these plots show that our model and true power spectra, again, match up pretty well, except for the lowest wave numbers. But again, this deviation at lower wave numbers does not significantly affect what we're doing. Now, to check that our power spectrum model is okay to use in the covariance integrals, we use a half inverse test. That's because the data is weighted by the inverse covariance, so we really need to make sure that we're getting the inverse of the covariance right. The half inverse test is defined in this top boxed equation. C is the covariance matrix of the 2-point correlation function. C true would be the 2 PCF covariance using the CAM power spectrum. C model is the 2 PCF covariance matching or using our model power spectrum. Ideally, we want C model and C true to match up. If they do match up exactly, then the half inverse test would give them null matrix. And this would only happen if our power spectrum model was exactly correct. Now, to numerically determine these C model and C true 2 PCF covariances, we use the second boxed equation, Cij. We have an integral of the power spectrum squared times these delta J1 functions, which are defined below, and they depend on spherical Bessel functions. Ri and R prime J are the two different separations that we're looking at in the covariance of the 2 PCF. And we use separations from 0 to 200 megaparsecs over H in the Boss number density. Here are the results we have for our half inverse test. We plot this for different number densities, and all of the color bars are over a different range. So in an ideal scenario where our power spectrum was exactly equal to the true power spectrum, then we would have ended up with a half inverse test showing the null matrix. Instead of the null matrix, we're seeing a sort of tridiagonal structure, but we are getting down to percent level accuracy with this. Here we are plotting this for different number densities, but in a real scenario, we would be able to take our analytic covariance, leave the number density and the volume free, and use that to calibrate our analytic covariance with the MOX. And by doing that, we expect that we could decrease the RMS even further. Okay, so this is showing that our power spectrum model is okay to use to calculate the analytic covariance matrices of the 4 PCF. Now, when we're looking at the covariance of the 4 PCF, we're looking at 2 tetrahedra. One will have a primary vertex and then side lanes R1, R2, and R3 to all 3 of the other galaxies. The second tetrahedra will also have a primary vertex with side lengths R1, 2, and 3 prime. S is the separation between the two primary vertices. When we look at the 4 PCF covariance, we really need to evaluate two different cases. The first case is where the primary vertices are coupled to one another, and all of the non-primary vertices are coupled to each other. Now, this equation gives an analytic covariance matrix for this first case. The important part to focus on is this integral over S, or the integral over separation between primary vertices. So we have C of S, which is a 2-point correlation function, and these F integrals, which I will define a few slides from now. But these F integrals depend on the power spectrum and spherical Bessel functions. So the two pieces that we need for case 1 of the covariance are the 2-point correlation function and the F integral. Case 2 is a bit more complicated because now we have primary vertices coupled to endpoint vertices. And again, what I want to focus on in this equation for the case 2 covariance is the integral over the separation between the two primaries. Now we have 4 different F integrals multiplied together. So for both case 1 and case 2, we need to evaluate the F integrals. For case 1, we also need the 2-point correlation function. Now, the 2 PCF is the inverse Fourier transform of the power spectrum that's shown in the first line. If we take our power spectrum model, insert it into the first line, we can just evaluate the 2 PCF analytically. And we end up getting this boxed equation. So we get a correlation function proportional to 1 over the separation between the two tetrahedra squared. The F integrals that we need for both case 1 and case 2 of the covariance are defined in this purple boxed equation. So we have integrals over the wave number of the power spectrum times 3 spherical Bessel functions. Spherical Bessel functions are combinations of sines and cosines, so they're highly oscillatory, and the 3 lowest order spherical Bessel functions are being plotted in the left side. On the right plot, we show the F integrand for 3 different combinations of L's. And we can see that these F integrals are highly oscillatory, but these are what we need to evaluate the analytic covariance. Okay, so we were able to put our power spectrum model into the F integral and evaluate this and get a result for it. Before I show the results, I'm going to go through a few definitions that are needed for them. First, we're going to have a quantity M that is bounded by different L values that come from the Wigner 3J symbols and their triangle inequalities. L, L prime, and L double prime are the orders of the spherical Bessel functions in the F integral. L is a sum from 0 up to L double prime. So M is really controlled by the orders of the spherical Bessel functions in our F integral. C depends on these orders, these L's, as well as Ri, which are the unprimed side lengths in the tetrahedron, and R prime J, which are the side lengths in the prime tetrahedron. W also depends on the L's, Ri, and R prime J. It also depends on L, M, A, and B, which will be shown a couple of slides from now, but L, M, A, and B are indices of finite summations. Next, we have R plus or minus, which depends on the unprimed and the primed side lengths, as well as the separation between the two primary vertices. F plus minus and F1 are 3F2 hypergeometric functions, so they're power series in terms of their arguments, which would be a power series in R squared or in 1. G plus minus and G minus 1 are major G functions. They're contour integrals in the complex plane, and these integrals depend on powers of their argument, so powers of minus R squared or powers of minus 1. Now, with these definitions, we can go to the result for the F integral. So the F integral, again, is defined in this first line. The result for this F integral using our model power spectrum is shown in this purple boxed equation. So you can see that we have 4 summations, but they're all finite summations. We also have different Heavisides, which are given by H. We have defined the Heavisides here so that they are only non-zero if the first argument is greater than the second argument. For the first Heaviside, that means this term in blue is only non-zero if 1 is greater than r plus. That corresponds to the highest region of S. So when S is between Ri plus R prime J up to infinity. The next term has two Heavisides multiplied together. So this is only non-zero when R plus is greater than 1 and 1 is greater than R minus. This corresponds to the middle region of S. The next term is only non-zero when R minus is greater than 1, and that corresponds to the lowest region of S. Finally, we have this 2 pi over a n bar S term that contributes over all regions of S. But the neat thing about this F integral result is that aside from this 1 over S term at the end, we will only have either the blue, red, or green term. We'll never have a combination of the blue, red, or green terms. So this breaks up our F integral result into different regions of the separation between the two tetrahedra. Okay, so just to wrap up what I talked about, we really need to get an accurate covariance matrix if we're going to do parity violation searches. An analytic matrix is useful when there are too many degrees of freedom to get the covariance from mocks. To get the analytic covariance, I modeled the power spectrum and numerically determined the covariance of the 2 PCF using that power spectrum to check that it was a suitable model to use. And then use the power spectrum model to evaluate the F integrals analytically that are needed for the 4 PCF covariance matrices. And in the future, I'm going to be checking the covariance model that I have with the analytic F integrals against the true 4 PCF covariance and hopefully applying this to actual parity violation analyses.